And let's use the same example that we did for the proton NMR. Lone pairs of electrons. So we've got our sample that we're going to be looking at here, and I've brought along the model again to show you what that looks like by a model. So we've got our methoxy group here on the bottom, on the number 4 carbon. We've got on the number 1 carbon here, we've got our ketone. So we've got a ketone, it's got a methyl group, we've got an aromatic ring, and we've got this ether group here. And so we've got all that contained within this simple molecule. Now, if we look at the total number of carbons, we see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9 total carbons. And so one might predict that we should see 9 signals in the carbon NMR. However, that would be wrong because we have a unit of symmetry, or symmetry element that runs through here that I showed you last time in the model. So if we turn these groups kind of perpendicular to the ring, you can see that there's a mirror plane that runs right through the middle that relates the 2 carbons to one another. So these 2 carbons are identical, and these 2 carbons are identical. So what we would expect to see then is, when I'll just label them A through G, we see A, B, C, D, E, F, and G. There's only 7 unique carbons. So we're going to see 7 signals in our predicted NMR spectrum that we're going to put together here. So this is D. Of course, this also is D because it's by mirror symmetry. This one is E. This one is also E. Okay? So by symmetry, we know we should see 7 unique signals. And if we imagine drawing out our spectrum, 0 to 200, let's look and see what we would expect. We've got an sp3 hybridized carbon there. We've got an sp3 hybridized carbon there, which is clearly different from this sp3 hybridized carbon. This one's attached to a ketone. This one's attached to an oxygen of an ether. So these 2 are clearly different. We've got an sp2. All the others are sp2. I'm not going to draw the arrows out, but B, C, D, E, and F are all sp2 hybridized. And so we're going to see all of those to the left of 100. We're going to see these 2 signals to the right of 100. So if we imagine our 100 here, we would expect to see 2 signals. Okay. One of them is going to be at about 27. The other one's going to be at about, put it a little more accurately, about 56. The one at 27 is A, and we can learn that from a table. It's attached to another carbon, whereas G, this one right here, is attached directly to an electronegative atom, which is going to pull it further downfield. So G actually appears at 56. Now, just on the other side of 100, we would expect to see our signals here for our aromatic ring, and we're going to see 4 of them because we've got C, D, E, and F, which gives us 4 unique signals. So we're going to see 1 signal, and then a couple of signals that are actually fairly close to one another, and then we're going to see another one that's a little further down. So the one here at about 114 is signal E. These 2 signals here that are at about 129 and 130, these are D and C. I'm just going to put D over C here. It's hard to tell which one is which, but D and C are actually fairly close to one another. And then this one, of course, is F. And it's the furthest downfield because it's directly attached to this electronegative oxygen. C and D are fairly close to this, so they're in this region, whereas E is the furthest upfield and just right after 100 at 114. And then we've got our ketone, and we would expect that to be fairly close to 200. And so that's signal B. And it's actually at about 197 parts per million. And so this is what one would expect to see for this particular example. So now we're going to get started into our problem-solving strategies and how we can actually use all of the information that we have in this laboratory to actually solve unknown structures or determine a structure from a set of spectra. Okay, so the structure is not going to be given to you. You're going to be given a series of spectra and some other data, and you're going to be expected to come up with a reasonable structure for that particular set of data. So we're going to be talking about our problem-solving strategy. And I like to call this 4 easy steps. So there's 4 steps to our strategy. Okay. And it's very similar to working with puzzles. Okay. Just like when you work with crossword puzzles or jigsaw puzzles or those big 1,000-piece puzzles, it's all about getting the pieces together, identifying what those pieces are, and then putting them together in a way that makes sense. Just like when you put together a jigsaw puzzle, it has to make a picture that looks reasonable. And that's how you know that you solved it correctly. The pieces fit together, but not only that, it makes a reasonable picture. And that's what we're going to be doing in our problem-solving strategy. Step number 1 is calculate the unsaturation number. Okay? And there's a formula for that in your lab manual.